Hello everyone, Mr. Hasty here. Today we're going to be talking about section 11.3 on limiting reactants. So let's briefly define a couple things pertaining to this section. So first of all, what is a limiting reactant? A limiting reactant is the reactant that will be completely used up in a reaction. What does that mean? Well, let's say we're making water. If we have, let's say, 6 hydrogen atoms, and 6 oxygen atoms. To make water, we need 2 hydrogens and an oxygen. So we make a water, takes 2 of our hydrogens and 1 of our oxygens. Make another water, 2 of our hydrogens, 1 of our oxygens. Make a third water, 2 of our hydrogens, 1 of our oxygens. And we can't make any more water. We're out of hydrogen. We have some extra oxygen left over. So in this situation, hydrogen is our limiting reactant. We are limited by how much water we can make based on how many hydrogen atoms we have. So what is the extra oxygen called? That's called the excess reactant. And it is simply the reactant that is not used up in a reaction. All right, we're going to move on to a couple examples now. So in our first example here, we're mixing sodium metal with water to produce aqueous sodium hydroxide. That means sodium hydroxide mixed with the water and hydrogen gas. So we have 100 grams of sodium mixed with 100 grams of water. We're going to determine the following. Part A, the limiting reactant. Part B, the mass of each of the products. And part C, how much of the excess reactant is left. This is quite a lot to do, so it's going to be a bit of a process. Anytime we're working with chemical combinations, the first thing we want to establish is a correctly balanced chemical equation. So we have sodium, which if it's in metal state, it's a solid, plus water, which is going to be in a liquid state. Let me read. And that's going to leave sodium hydroxide, which is NaOH. And I know that because sodium's a +1 and sodium's a +1 and hydroxide's a -1. It says it's aqueous. And hydrogen gas. So we know that hydrogen gas is H2. So let's balance that out. I have 1 sodium, 1 sodium. I have 2 hydrogen, but I have 1 hydrogen here and 2 hydrogen there. So I need to double this because the left side can only have an even amount of hydrogens. So I need to double the sodium hydroxide, meaning I have now 2 sodiums. So I need 2 sodiums on the left. I have 2 hydrogens on the left, but I have 4 hydrogens, 2 from the sodium hydroxide and then 2 from the hydrogen gas. So I need to double my water. So I have 2 sodiums, 4 hydrogens, and I have 2 sodiums and 2 and 4 hydrogens on the right. I also have 2 oxygens on the left, and I have 2 oxygens on the right. So this is our balanced equation we're going to work from. Part of my screen got cut off here. Let me fix that real quick. There we go. All right. So the first thing we have to decide, the left side is the reactants. We have to decide which one of those is the limiting reactant. And the way you do that is by comparing how much of each substance you have to work with in moles. So for part A, I want you to note that we have 2 atoms of sodium combining with 2 molecules of water. That means we need the same amount of sodium metal in moles as we do water moles. Because they both have the number 2 here, we need the same number of moles of each one for the reaction. So we're going to start by converting sodium and water into moles from their masses listed in the problem. So if I have 100 grams of sodium, I get on the periodic table and I find out that 1 mole of sodium has a mass of 22.990 grams. Telling us that we have 4.350 moles of sodium. So for the water, I have 100 grams, 100.0 grams of H2O and 1 mole of H2O. Now remember, we have to add up 2 H's and an O to find our molar mass. So that's 1 point each off our periodic table. Each hydrogen is 1.008 and 1 oxygen atom is 15.999. So let's add that up. And we get 18.015 grams H2O. Do that calculation. We get 5.551 moles of H2O. So, which one's our limiting reactant? Well, we needed 2 sodium atoms for every 2 water molecules. Remember, moles and particles can be thought of in similar ratios. So we need the same amount of moles of sodium as we do water. Since we have less sodium, sodium is our limiting reactant. We have more water than we need and less sodium than we need. So that concludes part A. We're going to move on to part B. I'm going to clear this. All right. We know we're starting with 4.350 moles of sodium. And that is the basis for all of our calculations for the products, because that's the thing that limits how long our reaction can go for. The work I'm about to do now comes from sections 11.1 and 11.2. Once we know the amount of moles in our product, we can use it to calculate the number of moles in our reactant. So we already have it in moles. We don't need to do a gram to mole conversion. We already did that. So we start from moles. If we have 4.350 moles of sodium, notice that there are 2 moles of sodium, and we're using the molar ratio here. 2 moles of sodium for 2 moles of sodium hydroxide. Cancel here and here. Now, we don't want moles of sodium hydroxide, we want grams. So we have to use our periodic table and determine how many grams 1 mole of sodium hydroxide is. So that's as simple as adding 1 sodium to 1 oxygen to 1 hydrogen. And when you do that, you get 39.997 grams sodium hydroxide. Now, when we do the calculation, remember, you multiply the numbers on top, divide the numbers on bottom. We are going to get 174.0 grams of sodium hydroxide. We're going to do a similar calculation for the other product, which is hydrogen gas. So we start with what we know, our limiting reactant, 4.350 moles of sodium. Now we got to apply our ratio here. There are 2 atoms of sodium, so that means 2 moles of sodium is going to be ratioed to 1 mole of H2 gas. Now, we don't want moles of H2, we want grams of H2. So we have to look on our periodic table and add up 2 H2s, which is 1.008. So we are going to get that 1 mole of H2 is 2.016 grams of H2. We do that calculation, we get 4.385 grams of H2. So now I know if I mix these two together, I'll get 174.0 grams of sodium hydroxide and 4.385 grams of hydrogen gas. The next question comes in is part C, how much of the excess reactant is left? So I'm going to clear this. So part C. Well, we know that if we have a limiting reactant of 4.350 moles of sodium, we can use molar ratios to determine how much of the water we will actually use. So in our equation, it says that 2 moles of sodium will react with 2 moles of H2O, and you could reduce that to 1:1 if you wanted. There's no reason. I'm just using the numbers that are our coefficients here. Now, this will tell us how much is used, not how much is excess, but then we can work backwards. So, 1 mole of H2O, we already did this calculation earlier, is 18.015 grams of H2O. We go through and we do our conversions, and we come up with 78.365 let's see, appropriately rounded, that would be 78.36 grams of H2O. Now, that's how many grams would actually be used. But we started with 100 grams of water, so we're just simply going to take 100.0 minus 78.36. Remember, the rules for sig figs here say that we're going to keep the smallest number of decimal places, which is 1 decimal place. And we get 21.6 grams of H2O left over. Now, how we can make sure this all comes together and makes sense is that what we start with has to be what we end with. The law of conservation of mass says that all the matter we start with has to equal all the matter we end with. So if we look, we started with 100 grams of sodium and 100 grams of water, so we should have 200 grams of material at the end. But if we look at the numbers we had, the sodium hydroxide was 174.0 grams, and the hydrogen was 4.385 grams. And that's not 200 grams, that's like 178 grams. But if we realize that not all of the water was used up, we still have 21.6 grams of water lying around, then we get pretty close to 200 grams. And that shows that it all works out. The law of conservation of mass can't be violated. All right. So I hope this has been helpful. We'll kind of do some more practice and work with this material as we move forward. Thank you, and see you again next time.